All right, so here's a little quick wrap up of the free fall lab. All right, so hopefully this is what you found. So you had a position time graph. Okay, and if you want to call it Y, that might be a good idea since it's vertical on your graph, right? And you saw it started at a position of like -50 or something around there. Okay, and it went up, I guess, to the 0. Went pretty much close to the 0, I think, like this. Okay, all right, so you can see that this is this parabolic shape, right? So this is a Y, or position is proportional to time squared. Okay, just like we saw in the dry ice puck lab, except for the other one had a positive parabola, all right? When you create your velocity time graph, Vy from this, okay, you can do it a couple different ways. So if you're thinking of the slopes here, right, the velocity is positive first, okay, comes to 0 at the top, and then the velocity is negative, okay? So it should look something like this, all right? And then this point here is the turnaround, right, where the velocity is 0, which corresponds to this point here where the direction changes. Okay, so just notice that those are the same points, all right? If you get this equation, okay, mine came out to be something like -4.9 meters per second squared t squared plus 3.3 meters per second minus 0.55 meters. Okay, something like this, right? Okay, so you should recognize this as this equation. Okay, Y final. Okay, so there was my initial position. That is my initial velocity. Oops, forgot a T. T minus. Okay, and this, okay, is 1/2 the acceleration. So you need to make sure that you understand that when you use the equation of a position graph, that constant in front of the squared term is 1/2 of the acceleration. Okay, so actually the acceleration is going to be -9.8 meters per second squared. All right, which you may recognize from freshman physics as the acceleration due to gravity on the Earth. All right, so that's how fast things accelerate when dropped on the Earth. All right, because we did this experiment on the Earth. All right, you can use 10. All right, even in the AP test, 10 is fine. Okay, so you might just kind of get in the habit of knowing it's technically 9.81, whatever, depending on your sea level height, but you can just use 10. All right, so how you'll see that here is you'll see the slope of this line should be -9.8. Okay, or you might think of it like this, meters per second, right? Because it's your Y over X. Okay, and so if you were going to create an acceleration graph, right, you would just have a negative value here at -9.8, constant acceleration, right? Because on the Earth, assuming no air resistance, we're going to say the acceleration is constant, okay? When the air resistance, that's coming soon, that's calculus, okay? But for now, it's just the acceleration is constant, all right? Okay, so if you threw it harder, right? So think about what would happen if you threw it harder. Okay, say it still started at, same place down here, right? You threw it harder, it would be faster at first, right? So it would start steeper, right, than it did before, right? And then it's going to end up, if you throw it harder, it's going to go higher, all right? And it's also going to take longer. So maybe like here was your old graph, okay? Your new one is going to go higher, and it's going to take longer. So let's see how that happened. So it's going to, because like the rate of change has to like be the same, right? So I think it would be, maybe more like this, right? So your turnaround would end up much higher, and it would happen later, right? Because it's going to take longer to slow down to that 0 point, okay? On your velocity graph, however, though, Vy, I kind of messed that up last time, okay? Before, your graph maybe looked, kind of like this, right? If I start it faster, it'll start here, okay? But the slope is still going to be the same, right? Because it's still the same acceleration. So the slope is going to be the same. Well, that's not the same, okay? And here again, I can see my turnaround happens later than it did in this position, okay? But the slope has to be the same because the acceleration is the same. That's the important part. All right, it starts faster, okay? And then mass does not affect the acceleration due to gravity. All right, and let's try not to just say gravity. Let's try to say acceleration due to gravity. Okay, so this acceleration of negative 9.8 meters per second squared, you could also call that little g if you wanted to, right? But it doesn't really matter. Just call it an acceleration, okay? And the mass does not affect it, all right? So this is the stuff that I want you to make sure that you present in your final product, right? That make sure you've kind of wrapped all of this up. And again, remember, this is for Earth, okay? G on the moon is about 1/6 of ours. It's about 1.7, I think, ish. Okay, G on Jupiter is about 27 times ours. So, I don't know, 270 meters per second squared. It's a lot more, okay? And the reason why, which we'll get into when we get to more of the gravitational unit, is based on the size of the body, right? So the moon is smaller, less, well, not really smaller, but less mass. Okay, the Earth is kind of like middle mass, and then Jupiter has a lot of mass, right? So it has a lot of mass, which gives it a stronger pull, you know, towards of the object. Okay, but we'll get into this more later. It's not really for this part. Okay, so I think that is the free fall wrap up of everything that you need. Hopefully we did this in class too, so maybe this is like your second go at it.